Hello. We're going to talk about several algorithms for searching and sorting. And so let's get started. First of all, the question is, well, why do we want to sort something into sorting means putting it into order, some order. The reason is that a lot of searches, several searches, are much quicker if they deal with sorted algorithms. So for example, suppose you had the 411 database of the entire United States, and the callers to the 411 database would expect almost instantaneous response. So they would expect a very fast search, but maybe 100 or 200 new phone numbers per day or per week or whatever are instantiated in this multiple million element data set. And so sorting could happen in the middle of the night, overnight, whatever, over the weekend, whatever. And as long as the search was very fast. So that's one reason we might want to use sorting first and then searching. And there are various reasons for using sorts. So we're going to talk about two kinds of sorts. Selection sort, they're both order n. In other words, they're fairly slow as n gets large. They're order n squared. And basically what we do with selection sort is we take the value in position 0 and we search through the rest of the array until we find the smallest value, and then we swap it with position 0, with the element in position 0. And then we know that position 0 holds the smallest element, so we go on to the next one. And so we start with position 1, and we find the next smallest element and swap that with position 1. And we proceed all the way through until everything has been sorted. So here's an example with five digits. We're going to sort them. So the first thing we do is look through, and we can see, being humans, we can see that 5 is the smallest, but the computer has to look one at a time. So it finds 5 and swaps it with 11. And then the next smallest element is 9, and it's already in the correct place. The next smallest element is 11, so it swaps with 17. And finally, 12 swaps with 17. We know that 17 is the so it has to be in the right place. So here's some code to do selection sort. So if we're looking backwards, the sorting happens in 3 steps as opposed to 6. But basically it's not any improvement. So then there's insertion sort, the second type. And in this case, we pick any item and insert it into the proper place in a sorted sublist. In other words, so we start out assuming that the first element is sorted, which it is because it's only one element. And then we take the second element and we put it in the proper place, either before or after. And then those 2 elements are sorted. And then we take the third element and put it into its rightful place, either in the middle or before or after. So here's an example of that same, well, it's a different list. No, it's the same list. So 11 is sorted, so we take 9 and sort it in before 11, because that's where it goes. And then we take 16. 16 is 9 and 11 are already sorted, so 16 should go at the end. 5 should go at the beginning, and 7 should go after 5 and before 9. So that's insertion sort. And there's the code for insertion sort. So here's another example after 3 iterations of insertion sort, or we call them passes. And so the next value is 23. 23 gets, so here is the next element to be looked at. And here's the already sorted list. Notice that's already sorted. So we take 23 and put it in its rightful place. We have to have a temporary variable, and it'll go right in the middle there. So 23 goes in its correct place, and then this list is sorted. So insertion sort takes twice as long compared with selection sort if the sequence is sorted backwards, but that's rarely the case. So now we have a sorted list, and there are numerous algorithms for sorting a list. Now we could search. And searching means finding a target element in a group of items called the search pool. And normally we don't return the target element, we return the index because, hey, we already know what the target element is. So there are 2 classic searching approaches. There's linear search and binary search. Now in class, I often, of course we don't have face-to-face class in this case, but I often go down the list and say, is your name Joe, is your name Joe, is your name, and it causes a little bit of giggling when I get to the girls and ask them if their name is Joe. And eventually we'll find Joe. And then I say, well, you've just done a linear search or a sequential search. You basically start at the beginning and use a for loop or some kind of loop to loop through until you find a match. Or you reach the end of the loop of the array. If you reach the end of the array, then you return a special value, maybe -1, to show that you didn't find it. So how many visits do you need to take? Well, on average, n over 2, maximum is n. Of course, best case is 1, but that's not really relevant. So this is simple code for sequential search. Now, binary search is interesting. So a binary search requires the array to be sorted in ascending order, in some kind of order, ascending or descending order. And you start with the middle element, and of course, if that's the desired value, then the search is over, but normally it's not. And so you divide the rest of the list into the greater or the lesser half. And you'll know, since it's sorted, whether the value you found, or whether the value you're looking for is in the lower half or the upper half, based on the value of the search. So basically, you're tossing away half of the search element. So here's an example. We're searching for 24, and again, we can see, being human, we can see that it's up to the right, but we don't know that. So we look in the middle element, 14. We say, well, 24 is greater than 14, so we can throw away the left half of the values and the 14 because we've already searched for that. And then we look for 22. We say, well, 24 is greater than 22, so we look at the right half. We can throw away the left half. And we do the same thing, and finally we find 24. Now this is 4 searches for 15 elements. So this is a log base 2 of n of 15, of 16. Well, it's 15 elements, so it's log base 2 of 16 is 4, and that's the maximum number we will ever have to look for. So here's some code to do a binary search, and if the two pointers, first and last, cross over each other, then we've decided that we haven't found the element. So now we're searching for 7, and 7 is not in the values, so we're going to look, and again we find that it's not in there. First has crossed over, last has crossed over less than first, and in the algorithm, so we know it's not in the list. Now, just like we saw in a minute ago, the arrays class contains sort methods if you have an array to start it with. Like I said, there are a lot of sort algorithms. There's quick sort. So the sort method in arrays uses a quick sort algorithm. Arrays.sort sorts the elements. Any element that implements comparable, just like we saw in the last video. So here are the sort elements. The natural ordering again is whatever the comparable interface requires compared to. So this is a discussion of compare to, which we discussed in the previous video. A negative number if A should come before B, a positive number if B should come after A, and if A and B are the same, they're supposed to be the same as equals. So a number of classes implement comparable. So if your array is composed of strings, then you can use Arrays.sort. We talked about this before. Rectangle is a class that does not implement comparable, and so you can't use Arrays.sort to sort it. Here's an example of bank account. What would you have to do if bank account was going to be sorted by increasing balance? Well, you'd have to implement compare to. Same thing with student. We saw this before. And the same thing with dog. So also you could do the same thing with collections like ArrayList and so forth. Arraylist.sort.